Let's try to solve this question here. The figure below shows an electric circuit consisting of a battery of EMF 6 volt and internal resistance 1 ohm. So they write it clearly over here. This is the battery. They label the EMF here to be 6 volt, the internal resistance here to be 1 ohm. Okay, and it consists of the resistor, two resistors and two switches. Okay, so you have one battery, two resistors and two switches over here. Okay, one thing I would like to talk about before we move on to talk about the question is that the battery here, we draw it as a symbol of a battery and also a resistor, right? Okay, it doesn't mean by we are connecting the battery to a resistor. No, okay, it's not like a battery and a resistor, we connect them in series like that. That's not the case. Okay, this internal resistance, it's inside this circle dotted line over here. It means that it is the resistance caused by the material of the battery. It is not a resistor that we install purposely into the circuit as a resistance. Okay, it is a side effect. You can think of it as side effect. It's a side effect of the battery itself, because the battery itself is made of certain material. So for charges to flow through that battery material itself also requires some more amount of energy. Okay, the process of letting the charge flowing through the battery material requires some energy, and therefore we can think of it as the battery material itself poses a little bit of resistance. Okay, so because the battery material itself poses a little bit of resistance, we assign a value which is called internal resistance to represent the battery material's resistance. Okay, it is not a specific component that is a that we call it as resistor. Okay, it's not a component that we install beside the battery. It is a side effect of the battery material itself. Okay, so they ask you to find a terminal voltage, which is what you can measure at the two ends of the terminal of the battery if you open switch 1 and you open switch 2. Okay, so open switch 1, open switch 2. Let's sketch a situation. Do we need to sketch it? Well, this is a situation. Okay, so this is diagram A for A. This is a situation. So if you like to think about the situation, EMF is equals to IR is what's being taken inside the battery, V is what's available outside. Okay, they are interested with the terminal voltage, so we can rearrange the equation to be V is equals to epsilon minus IR, and from there we know that there is no current flowing inside the there's no current flowing because both of the switches are open. If they are open, then current cannot flow through, right? This is an incomplete circuit, therefore your current will be equals to 0. So for sure you see that your terminal voltage will be equals to the electromotive force, and that's why the value here will be equals to 6.0 volt. Okay, very straightforward. This is what will happen if you open the two switches, causing no current to be flowing through the battery. Okay, if there's no current flowing through the battery, then there's no charges going through the battery material, right? So if there are no charges going through the battery material, there are no energy used to pass through the battery material. So if there are no energy being used to pass through material, so all the energy being supplied by the battery is available to be given to the external circuit. So what we measure here, what's available for the external circuit, is everything that is being supplied by the battery. That's why the terminal voltage is equals to the electromotive force. Okay, so let's look at question B. S1 is closed, S2 is open. Okay, so let's sketch it out. Okay, S1 is closed, S2 is open. So S2 here have to be open. It is S1 that needs to be closed. Okay, so 6 ohm, 3 ohm, S1, 6.0 for EMF, 1 ohm for internal resistance. Okay, let's enclose our battery. Okay, so we can see that what we have here, internal resistance is still 1 ohm, but right now because the lower branch over here, it's connected, it's closed, therefore current can flow in this loop over here. Because current can flow in this loop over here, then we need to consider this 3 ohm here to be our external resistance or resistance in the external circuit. Okay, we don't need to consider 6 ohm as the resistance of the external circuit because this path over here is not available for current to flow as the switch is open. So there's only this resistance that needs to be involved here. Okay, so if you use back the same equation, epsilon is equals to IR plus V. Okay, you might should we think of you want to do your substitution of EMF in, then you want to put in your internal resistance, then from there you can get your terminal voltage. No, you cannot do that because the problem is you don't have your current. So because you don't have your current, then probably you need to go determine the current first. How do you determine the current? Well, there's another equation that you can use, right? You can expand your internal volt. You can expand your terminal voltage over here to be equals to IR effective. Okay, R effective means by anything that is connected to the battery at the external circuit. So the terminal voltage is what's available for the external circuit, right? So it's equals to current multiplied by the effective resistance or the combination of resistance outside the battery. Okay, so now you can factorize the current. So this will be R plus R effective. Okay, doing so, you can do a substitution, I believe. So this will be 6 volt EMF. Current is not, we don't know the current, but we have our internal resistance, which is 1 ohm, and our effective resistance is just 3. Okay, effective resistance here doesn't include the resistance caused by the battery material. We're looking at the external circuit. After we combine all the resistance in the external circuit, what is the effective value? That will be effective resistance. Okay, again, we don't need to consider 6 ohm because that branch is not available for charge to flow. So we are only talking about this 3 ohm over here. That's why there's only one resistor available, right? So that will be our R effective. Okay, so from here, if we do a calculation, you get our current to be equals to 1.5 M, I think. Okay, current is equals to 1.5 M. And if you have your current already, now if you want to determine your terminal voltage is V, right? Just equals I R effective. Okay, so if you do a substitution, this is 1.5 multiplied by 3, this will be 4.5 volt. Okay, so this is the amount of energy that 1 coulomb of charge can supply to the external circuit of the outside the battery. Okay, so that means by 4.5 volt of the 6 volt will be given to the outside, the circuit outside here. Whereas if you take 6 volt minus 4.5 volt, you have 1.5 volt, right? That 1.5 volt is the energy that 1 coulomb of charge will be that the 1.5. Let me write it out. Okay, EMF is 6 volt. Okay, then your terminal voltage is 4.5 volt. Then you have your I small r here, which will be equals to EMF minus terminal voltage. That will be equals to 1.5. Okay, so what can you see over here? The battery is going to supply 6 joule of energy to every coulomb of charge passing through it. So if 1 coulomb of charge passes through it, it will receive 6 joule energy from the battery. Okay, so the 1 coulomb of charge will be holding 6 joule of energy. Okay, every 1 coulomb of charge that passes through a battery will receive 6 joule of energy. But when it is passing through the battery, because the battery material itself poses some resistance, even though the battery has the intention of supplying 6 joule energy to every 1 coulomb of charge that passes through a battery, but the journey of passing through the battery material itself will be using 1.5 joule as well. So every 1 coulomb of charge that is passing through the battery, even though it receives 6 joule from the battery, it will immediately use up 1.5 joule of energy just to get through the battery. So at the end of the journey, when you're exiting a battery, you are not having 6 joule of energy in the battery, in the charge, a 1 coulomb charge hand. Okay, you already lost 1.5 just to get through the battery. So you only have 4.5 joule available for the charge to give to the outside circuit before coming back at the negative terminal. Okay, so receive 6 joule, wasted 1.5 just to get through the battery, left with 4.5 to be given to the external circuit before getting back to the negative terminal. That's the idea of how we see EMF, how we see I small r, how we see terminal voltage. Okay, we see EMF as supplied by the battery, we see IR as what's being used inside the battery, we see V as what's available for the external circuit. Okay, so let's continue in C. S1 and S2 are both closed. Let me sketch the diagram. Okay, battery, internal resistance, label this as 6 volt, label this as 1 ohm, okay, S1 is closed, right? S2 is closed as well, so we can just sketch it like this. 6 ohm, 3 ohm, S1, S2. Okay, so this is our circuit here. Since both of the switch are now closed, we have to consider both of these resistance together to be our effective resistance. Just now one path is not available, but now both paths are available, so we have to combine them to get our effective resistance. Okay, so we have to find R effective. R effective here is basically a combination of 6 ohm and 3 ohm being connected in parallel. So in parallel, we have to do this equation. 1 over 6 plus 1 over 3. Then to flip the value here. So if you do so, I believe you'll get an answer of 2 ohm. So that will be your effective resistance. Next, we are going to do a similar thing. We are going to do EMF is equals to I R plus R effective. Okay, you can do a substitution. It's the same thing as what we did in question B. Okay, so I is what we need to find. This should be 1 ohm plus R effective 2 ohm. So you get your current to be equals to 2 ohm. 2 ampere, sorry. So you get your current to be equals to 2 ampere. You can find your terminal voltage by substituting I with 2 ampere. The effective resistance here will be 2 ohm. So we can see that the answer is 4 volt. Okay, so this time again the battery is going to supply 6 volt. What's available for outside is what's available for external circuit is only 4 volt. So that means by your battery itself is going to consume 2 volt. Okay, for every it's going to consume 2 volt. So battery supplies 6 joule energy to every coulomb of charge that pass through it. Every coulomb of charge that pass through battery will be wasting 2 joule just to get through a battery. So what's available for the external circuit is 4 joule of energy for every single coulomb of charge. Okay, every single coulomb of charge that reach the positive terminal will have 4 joule energy ready to be given to the external circuit before coming back with 0 energy left. Okay, so that's the basic idea. So for question B and question C, right, there's actually a shorter way of solving this question. You can solve it using the concept of potential divider. Okay, for this situation here, you can think of it as one single battery, an ideal battery with 2 resistance. Okay, with 2 resistance. You are interested with the voltage across this external resistance. You are not interested with the voltage across the internal resistance. So because you're interested with R over here, you can use the potential divider idea by saying that if I want to know what's available for the external circuit, you can use potential divider and say that this is R. Okay, you know that this input here will be shared between small r and big R. Okay, but we are interested with what's available for large R, the external resistance over here. Okay, we know that it will be shared between internal and external resistance, but we are interested with the external one only. Okay, so who's the input? The electromotive force. Okay, so this is one way of solving a question using a concept of potential divider. Here we just use the concept of Ohm's law basically, but here we use the concept of potential divider. Both works, okay, both use a similar concept actually. Okay, so outside you have 3, external circuit you have 3, internal resistance is 1, external resistance is 3, so it will be 3 over 4 multiplied by 6. 3 over 4 multiplied by 6 is just 4.5. Okay, so this is one way of solving question B. So if you apply the same concept for C, it will be V is equals to R. Okay, let's write clearly this is R effective because there's 2 external resistance involved. R plus R effective multiplied by the electromotive force. We already determined the effective resistance to be 2, so this will be 2 over 1 plus 2, so this is 2 over 3 multiplied by 6, and from here you are able to get 4. Okay, so these are 2 equivalent methods to solve the question. Of course, you see that this is shorter, but it requires you to be very clear how to apply the concept of potential divider. Both are fine, both will let you determine the answer correctly as well. Okay, so that's it for this question. Thank you very much.